They were different test results. Some very good, some very bad. And 8 people got a perfect score of 100. So just more than 10% got perfect score. So this will help you to place you in this class. Now, this average and median are somewhat low. So I will compensate for this, adding 10 points to every score. So I will not put this in the system, but when I compute the final grades, the test scores will be increased by 10. So if you have, let's say, 60, this means that you have really 70 points. So this should help with your grades a little. So again, you can add 10 points to every score, to your test score. Okay, so now let's go and continue the lecture. So now we are going to, what was the section? I believe we did 1.1, 1.3, and I think that's 11.4. We did one page last time, so let's continue. So tangent planes. Again, I will ask the usual question. Can you see?
Yes.
This slides, right, okay. So tangent planes and linear approximations. You will see what is this. So again, so this is what we covered last time. You have a plane, surface S, described by the equation z equal f of x, y. So of course, this surface may look like this kind of blue surface here. And we are assuming that the function is kind of smooth, has continuous first partial derivatives. And we consider point P with coordinates x0, y0, z0. Z0 is f of x0, y0, which is on this surface. And now we consider 2 curves. We intersect this surface with a plane y equal y0. So where y is constant, that's a plane, and x equal x0, that's again the plane. So intersecting the surface with this curve and this curve, we are getting 2 curves. So C1, this is this blue one, is the intersection of the surface with the plane y equal y0. And this red curve is the intersection of the surface with the plane x equal x0. Now, we can compute tangent vectors at this point here to those curves. This was discussed already before, and you remember tangent vector, the first tangent vector, as I call it, T1, is 1, 0, and partial derivative with respect to x. Again, I justified this formula using 2-dimensional picture. But I told you, even if you miss the justification, just you have to remember that the first tangent vector is 1, 0, fx. And tangent vector to the second curve is the other way around, 0, 1, and partial derivative with respect to y. So those are 2 tangent vectors to those curves. Again, justification was given, but you have to know the formulas for those. You may be asked to compute such things on the web work and so on. And now we would like to write the equation of the tangent plane, this kind of pink plane here. To write the equation of the tangent plane, you need a point, and we have a point, and you need a normal vector. Of course, you can get a normal vector if you compute the cross product of T1 and T2. So that's a normal vector to the pink plane. So the normal vector is T1 cross product T2. And computations are skipped here, but of course, if you substitute, you use this kind of 3 by 3 determinant. you can verify that the normal vector is minus fx, partial derivative with respect to x, minus fy, partial derivative with respect to y, and 1. So that's a vector in 3 dimensions, of course. So first component, second component, and the last component is equal to 1. And of course, now once you have a point and normal vector, of course, the equation of the plane is r minus r0 dot product n. And if you compute this, you will get, well, so vector r minus r0 has coordinates x minus x0, y minus y0, z minus z0. And this vector has coordinates here. So if you compute the dot product, you will get minus fx, x minus x0, minus fy, y minus y0, and plus 1, z minus z0 equals 0. If you solve this for z, you will see that z, the equation of the plane is z is equal to z0. Z0, of course, is f of x0, y0, plus fx, partial derivative at the point x0, y0, x minus x0, plus fy at the point x0, y0, y minus y0. So that's the equation of the tangent plane. Again, the derivation is here, but you will have to use this formula. So kind of, as you see, remember this formula, put it on a piece of paper and so on, kind of. That's the equation of the tangent plane. Again, derivation is here, but you will be responsible for using just this formula. So here is example. Find an equation of the tangent plane to the paraboloid. Well, this curve z equal 3y squared plus x squared, it's paraboloid. It looks more or less like this blue surface here. At specific point, so x is 2, y is 1, and z, of course, if you substitute 2 and 1, you'll get 3 times z, 3, y is y, no, yeah, so, okay, substituted, y is 1, so you get 3 plus 2 squared, it's 7. So, of course, this point, this 7, you can compute from here. So, y is 1, x is 2. If you substitute 1 and 2 here, you get that the last component, z, is 7. So, of course, the point 217 is on this surface, on this parabola. This is more or less here. Okay, so we have a point, x0, y0, z0, that's 217 given. Now, to compute the tangent plane, we need partial derivatives. Fx, well, derivative partial with respect to x is just 2x. You treat this as a constant, so fx is just 2x. If you compute this at the specific point, x0 is 2, so of course fx at the specific point is 4. Well,
Professor,
yes?
Does the partial derivative of, like, with respect to x and you input 2, does that just calculate basically like the change of just x at that specific point?
Yeah.
Or so, the rate of change, just to say, sorry.
Yes.
Okay, I was just curious if that's what it indicated. Thank you.
So you understand, okay. So now partial with respect to y. Well, now y is variable, you treat x as constant. So partial with respect to y will be 6y. And then we are interested in this value at specific point. Well, y is 1. So the partial derivative at the point 2, 1 is 6. And then z is equal to z0, well, the z0 is 7, plus fx at this point, x minus x0 is 2, plus fy at this point, y minus y0 is 1. Well, if you simplify this, you will see that z is equal to 7 plus, if you substitute, plus 4 x minus 2 plus 6 y minus 1. Again, you can still simplify this, and z is equal 4x plus 6y and minus 8 and minus 6 and plus 7. This is minus 7. So that's the equation of the tangent plane at this point. So here is kind of just tangent plane. Of course, if you kind of zoom, approximates the surface in the neighborhood of this point. You can see that the tangent plane and surface, well, they are different, but at this point they are the same. But of course, in the neighborhood, if x and y are not too far from x0, y0, the tangent plane approximates this surface. So kind of you can get it just by zooming in. You see that when you zoom in, the difference between tangent plane and the surface is getting smaller and smaller. And this will lead to the notion of so-called linear approximation. So let's see. Also, here is linear approximation. So the tangent plane to the graph of this function at specific point is this. So that's what we had on the previous pages. And now, that's of course linear function. Z depends on x and y in a linear way. So we will call this, so this, the notation sometimes used is L of xy. So that's this function we call by L of xy. And we call this linearization of the function or a linear approximation or tangent plane approximation. So this is kind of terminology here. So again, this function here, of course, is approximates. So f of xy can be approximated by this linear function in the neighborhood of this point x0, y0. So of course, this is approximation. At x0 and y0, this is exactly equal. But if x0, if x and y are different from x0, y0, this plane is, roughly speaking, equal to the function if the point, if you are not too far from the point x0, y0. Again, terminology is the following. L of xy we call linearization of function f at x0, y0, or we call this function linear approximation to the function f, or we call this tangent plane approximation. Those are synonyms. So kind of just to see it. So this L, X, Y has three different names. You can call this linearization, you can call it linear approximation, you can call it tangent plane approximation. Just three different terms for the same thing. So again, what I said, the linear approximation is a good approximation when the point xy is near x0, y0, provided that the partial derivatives fx, fi exist and are continuous, which means that the function is so-called differentiable. So if the function is kind of nice, yeah, differentiable means nice. If the function is kind of smooth enough, L approximates f in the neighborhood of the point x0, y0. So linear approximation. So again, three different names for this. Here is the example. So we have a function f of xy square root x plus e to the power 2y. There's no picture, just this is of course some surface. And now, explain why the function is differentiable at a0 and find the linearization. Well, it's okay. So y function is differentiable. Let's compute partial derivative with respect to x. Partial derivative with respect to x is 1 over 2 square root x plus 2y. Of course, you see that this is continuous function in the neighborhood of the point 8,0. At the point 8,0, it has even the value 1,6 if you want to check. But of course, you see that in the neighborhood of this point, this is a nice function, continuous function. So fx is continuous function. Fy, what is fy? Fy is 1 over 2 square root of this, and derivative of the inner function is 2 e to the power 2y. 2 cancels. So you can cancel 2 here. But again, you see that in the neighborhood of the point 80, this is a nice function, continuous function. So this means that the function is differentiable. And of course, the values of those things at the point 80, fx is 1,6, fy is 1,3 at this specific point. Easy to check. Again, both partial derivatives are continuous at the point, so f is differentiable. And now, of course, what is this plane? Z equal L of xy is equal. Well, z0, well, that's f of x0, y0, plus fx at this point, x minus 8, yeah, the point we are interested is 8, 0. And plus fy at this point, 8, 0, y minus 0, which is y. So if you substitute everything, of course, so just compute f of, if this is 8 and this is 0, that's 9, so this is 3. So z0 is 3, plus partial derivative is 1,6, x minus 8, plus 1,3, y minus 0. So simplifying, you see that this is, if you multiply and simplify, you'll see that L of xy, a linear function, is x over 6 plus y over 3 plus 5 over 3. And just check it, yeah, that's the same thing. So that's the first. And second, use this linearization, use this to approximate the function at the point 7.5 and 0.2. Of course, 7.5, 0.2 are not very far from 8, 0. Well, here the difference is 0.5. The difference between 0 and 0.2 is 0.2. So of course, so what is the approximation? Well, let's compute this function at this point. So we compute L at the point 7.5, 0.2. So if you substitute, this is 7.5 over 6 plus 0.2 over 3 plus 5 over 3. Use your calculator. This is roughly speaking 2.9833. And now you can check actual value of the function. Well, compute f of 7.5, 0.3. That's the formula. Again, use your calculator. You will see that that's roughly speaking 2.9986. So of course you see that this and this is different. But the difference is more or less kind of 100. They differ by 10 to the power minus 2. So of course, this is not equal to this, but this is kind of close to it. You could say that we have kind of 2 decimal digits of accuracy. 2.9 is here, 2.9 is here. The difference is in the third digit. You have 8 here, you have 9 here. So kind of, in some sense, we have 2 digits of accuracy, using kind of the terminology we use in the numerical analysis. Again, you will have similar things. You will have to do similar things on the web work to approximate things. So of course, if the point, this point is not too far from here, so we are getting some approximation. Of course, if the point would be closer, the approximation would be even better. So again, the tangent plane at the point P, A, B, and Z is f of A, B. This is an approximation to the function Z equal f of xy for x, y near A, B. So that's kind of what we discussed. So here, f of xy is roughly speaking equal to Z, which is f of AB, plus fx, that's the tangent plane, fx at the point AB, x minus A, plus fy at the point AB, y minus B. And now it's some kind of terminology. So in other words, if you take this on the other side, you can say, you can see that f of xy minus f of AB is approximated by fx times this plus fy times this. Now we call this difference of f values by delta f. So f at the point minus f at the different point, that's a difference of f values. We call this delta f. Here is x and here is x0. We call this difference delta x. Here is y, here is y0. We call this difference delta y. So of course, using this thing now, we can say that the delta f, the difference between the function values, is roughly speaking partial derivative with respect to correct time delta x plus fy delta y. And now, if you pass with delta x, delta y to 0, so letting delta x and delta y approach 0, well, yields the definition. If this goes to 0, we call this dx, dy, and we will call this df. And such a object is called differential of the function f. So again, passing with x minus a, so if x tends to a and y tends to b, of course, the delta x goes to 0 and delta y goes to 0, then such a thing is denoted by df instead of delta f, and this is called differential. So the differential df is fxab dx. This is this infinitesimal quantity. This is a quantity which goes to 0, plus fy at the point ab dy. And that's interpretation, geometric interpretation of this. This is kind of the difference between, so in other words, df approximates delta f as dx and dy are small. And here is the picture. You see, so here is the surface again, the blue one, and the tangent plane is a pink one. So here is a point AB, x is A, B, so kind of this is a point AB, and then the difference between, so df is kind of this value here, the delta f is this value here. So you see that this approximates this. If delta x, delta y are small, this is close to this. The difference between those two things disappears. So this is kind of some geometrical interpretation. So differential approximates the difference between function values. But again, that's the definition of a differential. So differential is defined by this quantity. And of course, the meaning is that df approximates delta f when dx and dy are small. Again, that's a three-dimensional picture. So always kind of, it's not so trivial to see things in 3 dimensions. Similar things hold in 2 dimensions. Then of course things are much easier to interpret. But here you need 3-dimensional picture to plot something like that. So here is an example. You will be asked to compute the differentials and so on, kind of. So z is equal to 5x plus y squared. Find the differential dz. Well, or if you call this f, then df, but kind of that's here another kind of name, dz. Find the differential dz. That's the first part. And second, use the differential to estimate the change in the function. This change is denoted by delta z when xy changes from 1, 2 to 1.05, 2.1. So in other words, dx and dy will be, dx will be 0.05 and dy will be minus 0.1. No, 0.1. It's increasing, yeah. So you see the difference between x values is 0.05. So delta x is 0.05. And the difference between y values is 0.1. So delta x is 0.05, delta y is 0.1. Okay, so let's do things. So to find the differential, of course, we had a formula on the previous page. You need fx and you need fy. Well, fx, of course, is 10x. Fy is 2y. So dz is fx dx plus fy dy. So dz is 10x dx plus 2y dy. And now we use this kind of approximation formula. Delta z is, roughly speaking, fx at the 0.12 delta x plus fy at the 0.12 delta y. Well, so of course, fx at the 0.12 is 10. Fx at the 0.12 is 10. Fy at the 0.12, well, y is to 4. And of course, delta x is, as we discussed, 0.05, 0.1. So substituting, delta z is fx, which is 10, 0.05, plus 4, 0.9. If you compute this is 0.9. And then you can compare this with an exact actual value. So delta z is approximated by 0.9, but now actual value. So f at this point minus f of this point. If you substitute, of course, that's easy function, and do your computations, you will see that that's 0.9225. Again, this and this is not the same, but the difference is more or less 0.02. So kind of just 2 times 10 to the power minus 2 is the difference between the true value and approximation.
Professor?
Yes.
I understand how the approximation works. All that makes pretty good sense. I guess I'm curious as to, it seems like getting the actual difference is even easier than getting an approximation, and it's accurate. So why would you want to use the approximation?
This is what I was going to say in a moment. Yeah, it looks like on those trivial examples, of course, you can get the true value kind of, but in many cases, when the function is complicated, it will be much easier to compute approximations than the true value kind of. So that's the reason. So of course, those are trivial examples for when the function is kind of like, looks like this kind of 5x squared plus y squared, what doesn't matter really. But for very complicated functions, it will be much easier to compute this than this. So that's the reason. So if you will take numerical analysis, and probably many of you will take kind of numerical analysis classes, and you will see that there will be one chapter in numerical approximation of functions, and then you will see more realistic examples when really it will be much easier to compute approximation than the actual function. This function can be highly nonlinear and so on, kind of just, you see, containing a lot of things, maybe expensive to compute. On the other hand, approximation is just linear function, which is usually quite cheap. But again, on those trivial example, of course, kind of just, you see, you can get the exact values kind of, yeah. But in general, for complicated functions, it will be easier to compute this than this. And you will see such examples. Those of you who will take numerical analysis, you will see such examples in numerical analysis classes. Okay, so now everything we did so far was in 2 dimensions. We have a function of 2 dimensions, like here, z equal 5x squared plus y squared. Well, you can generalize this to any number of dimensions. And here is 3-dimensional example. So we'll just use kind of just some common sense generalization of this to 3 dimensions. So let's check this example. So 3-dimensional example. And here is kind of some kind of just exercise. The dimensions of a rectangular box are measured to be 70 centimeters, 55 centimeters, and 30 centimeters. And each measurement is correct to within 1 point of centimeters, 0.1 centimeters, 1 millimeter. So when you are measuring the box, the error you are making each dimension is at most 1 millimeter. And now, use differential to estimate the largest possible error when the surface area of the box is calculated from these measurements. Okay, so that's the example, and now let's solve it. So to solve it, let's introduce the notation. Let's call x, y, and z, now as we see 3 variables, the dimensions of the box. Yeah, so kind of just the rectangular box, of course, has 3 dimensions. Let's call those dimensions x, y, and z. You see that we have now 3 dimensions. And now we would like to play with surface area. So of course, surface area is a function of these dimensions. So surface area depends on x, y, and z. And what is the surface area? Well, of course, you have 2 bases. The area of the base is xy. So this is the bottom of the box and top of the box, 2xy. And of course, you have 4 sides. 2 sides has the dimensions yz, and 2 sides has the dimensions xz. So the surface area of a box is 2xy plus 2yz plus 2xz. So hopefully that's clear. Yeah, that's just surface area of rectangular box. The volume would be x times y times z, but the surface area of the whole thing of the box is, again, you have bottom of the box is surface area is xy, top of the box is xy, together 2xy, and those are sides. 2 sides with dimensions yz and 2 sides with dimension xz. So surface area is a function of 3 variables and has the formula 2xy plus 2yz plus 2xz. So okay, let's compute the differential, and then later we will replace this by delta s. So differential ds is partial derivative with respect to x dx, partial derivative with respect to y dy, plus partial derivative with respect to z dz. Well, so of course, let's compute those partial derivatives. Partial derivative with respect to x, well, 2y plus 2z, 2y plus 2z dx. Partial derivative with respect to y, well, 2x plus 2z dy. And partial derivative with respect to z is 2y plus 2x, 2y plus 2x dz. Okay, and now delta x, well, that's given. The measurement is correct to up to 0.1 centimeters. So this means that the absolute value of delta x, so delta, the measurement can be just, let's say, 70 centimeters plus 0.1 or 70 centimeters minus 0.1. In other way, absolute value of the difference in x is bounded by 0.1, and that's given. Same thing for delta y and delta z. So delta x, delta y, and delta z are bounded by 0.1. The biggest value they can take is 0.1. Of course, sometimes they can take value 0. Then you see delta x can be also 0, 0, 0. But the worst case scenario is when delta x is plus minus 0.1. Delta y plus minus 0.1, and delta z plus minus 0.1. That's the worst possible case. So to find the largest error, we will consider this worst possible case. Well, so to find the largest area, well, let's assume that we have this kind of the worst case, the delta x, delta y, delta z is 0.1. That's the worst case scenario. And x is 70, 55, and 30, that's given. So of course, now delta s can be approximated by 2x plus z. Well, when you substitute, you get this 0.1. Substitute, here is again x, and here is y and z, and x, and z, y and z, x and z, and y and x. And you multiply everything by 0.1, that's the difference, 0.1, 0.1. And you see that the delta S, the error we are making is 62 square centimeters. So the biggest possible error you will make is 62 square centimeters. Of course, the area is kind of much bigger, kind of just, yeah, but so that's the biggest area you will make. Of course, if you are lucky and your measurement is smaller, kind of, but that's the worst case scenario. Okay, let's put it this way. The biggest error you will make, you can make is 62 square centimeters. Quite big, yeah, but still, those are the computations. Okay, so this is all. Any questions here? We can go to any kind of slides if you want. So any questions? Hopefully that's kind of reasonable. Again, so you have to know basically a few formulas here. You have to know the formula for the tangent plane. It's on slide number 1. And of course, this thing here is also denoted by L, X, Y. And as I mentioned, it has 3 different names. So this thing is called linearization, or linear approximation, or tangent plane approximation. Those are synonyms. So kind of you can see, you may get any of those terms on the web work, or maybe kind of sometimes they will use this term, sometimes they will use this term, or sometimes they will use this term. So be aware of this. There are 3 different names for the same thing. So L of xy, this is this kind of linear function. This is this kind of plane. Another, you could call this also just, that's an equation of the plane. Z equal L of xy is equation of the plane. Okay, so maybe kind of, let's just look, let's look maybe now at the next section, and we will not finish this, but kind of let's maybe start. Oh no, so let's. So we covered tangent plane. So chain rule. So let's check it. 11.5, the chain rule. Maybe just let's start maybe 1. This thing is coming back. Let's see. Chain rule, it's here. Okay, chain rule. Can you see it?
We can see it.
Okay. So again, just maybe just, we will cover this next time, but let me on the, maybe just one thing. You know, of course, the chain rule in 1 dimension. Also, that's kind of what probably you know. But then we will have chain rule in. So here we have the following sets. So of course there'll be a lot of variants of this chain rule. Okay, so that's first case. So there'll be different variants of the chain rule. So that's the simplest case. Well, maybe not the simplest kind of, but we have a function of 2 variables, z equal f of xy. We are assuming the function is differentiable at some specific point. Well, this point is called AB. So this means that the partial derivatives exist near this point or are continuous. So that's the assumption. We have a function which is kind of, we say this smooth. We have a smooth or a regular function. Regular means that the function is differentiable, a partial derivative exists kind of in the neighborhood of this point. And then we have, if you assume that also x is a function of another parameter t, and y is a function of parameter t. So x is some function g of t, and y is some function h of t. So of course, if you substitute here, you will get that z will be f of x of t, y of t. Z will be a function of one variable. But of course, it's defined in this complicated way. And then, so again, think about this, that x depends on one variable and y depends on one variable. Later, you will see that x may depend on two variables, three variables, and so on. But the simplest case is, let's assume that x depends on one variable, let's call this variable t, and y depends on one variable, again, call this variable t. And the functions are g of t and h of t. Again, if you substitute this thing here, you get f of g of t and h of f of g of t, h of t. This would be a function of t. So z would be a function of t. And now you would like to compute the derivative of this function with respect to t. And the chain rule tells you, well, to compute this derivative, you compute partial derivative of this with respect to x, and then derivative of x with respect to t. So that's the chain rule. dz over dx, dx over dt, plus then partial derivative with respect to y, dy over dt. So that's the chain rule. One variable case. We have two variables here, x and y, but each depends on one independent variable t. That's the chain rule. Here is kind of tree diagram. When you have a z, you can that's kind of some symbolic picture. That's d over dx. This is d over dz, and then you have d over dt. This is something is messed up here. This is dt. You don't see this kind of word. So here is variable z. The node is x and y, and here is tt. So now to compute the total derivative, dz over dt, you go this way, plus you go this way. So that's kind of symbolic picture. Yeah, you see here. To compute this dz over dt, you go this way, d over dx, and then dx over dt, plus d over dy, dy over dt. You have to exhaust all the branches. So that's kind of the graphical interpretation of this formula. So multiply along each path, this times this, and sum the contribution of both paths. So if you go like this, you multiply. And then you sum contribution of two paths. And that's the formula. So again, this is a formula. This is a graphical interpretation. This graphical interpretation doesn't matter for this simple case, but you'll see that this will be quite useful when we have more complicated situations. Okay, so this is maybe all for today. Just try to read maybe the slides in advance. It will be easier to follow. Yeah, you'll see kind of there's a lot of more complicated pictures and so on kind of later. You see here, you see the pictures are getting, look. So kind of just, you see, sometimes this will be useful kind of to use this thing. It will be easier to kind of interpret things. But that's all for today. So we just covered one slide. I will go over this again, but then you see, we will have, of course, a lot of other cases, more complicated. So again, x may depend on two variables, three variables, and so on. Also, the function itself may be function of 2, 3, 4 variables, and so on. Kind of. So you may have a lot of, we'll discuss a lot of more complicated situations next time. So this is all for today. So thank you. Any questions about this and the test and so on?
No questions for me. Thank you, Professor. Have a good day.
So thank you.
Thank you, Professor.
Yeah.
For the test,
Yes.